Okay, so we're going to use MATLAB to help us with that example 2 in terms of determining the constants and doing some of the integration and differentiation as the case may be. Right, so just as a prelude, we have a MATLAB screen here. So MATLAB does calculations, or is capable of doing calculations in the symbolic form, meaning that this is the form in which we are accustomed to in writing equations, like how we would write equations. Right? To ensure that MATLAB is able to do this, it must have installed the symbolic toolbox, which is installed already in the different MATLABs we have on campus. So to activate it, we say okay, syms. So it tells MATLAB now that anything that follows is symbolic. So we can say X. So you notice the X now is purple. So hit enter. So it stores now in the workspace X, and it stores it as a 1 by 1 sim, meaning that is a symbolic notation. So we are custom writing equations. For example, we could say y is equal to 2x squared plus 3, for example. Right, so that's our equation. If it is we want to get our equation written in such a way that we could visualize it better, we could use the command pretty y. Right, so it writes it in a kind of form that we could see the superscripts a little clearer. It also works good with fractions. Right, so we have y is equal to 2x squared plus 3. So if we want to differentiate this, we could use the command diff as to differentiate, open bracket. So we want to differentiate y, comma, with respect to x. So when we hit enter, we get the differential. So of course the differential of 2x squared plus 3 is 4x. Right? Now, if we want to integrate, we go int. That's the function for integrate, open bracket, y with respect to x again. Right, so this is the integral of that, of y. Right, we could again use the function pretty. Now, what I do with my command history on this side here, that's how I set up my MATLAB. I could just drag this across here. Right, so the variable name is answer, ans. Right, so every time you do an operation, MATLAB it stores it as answer. If you were to do another operation, well, then it will be rewritten as answer. Right, so we want to write this in a format we could see, so it will be pretty answer. So you could say it writes it in a form that we could actually, it's easier to make out. So 2x cubed on 3 plus 3x. Right, now in integration, we will of course have the constant, so MATLAB doesn't do that. It doesn't put like plus c. Right, so when we transfer this to our written script, wherever it may be, we will have to include our plus c. Right, so we're going to use this integration, differentiation, and the symbolic sense to actually do example 2. Okay, so we look at the example 2, right, from the notes. So example 2 is a circular plate. It's fixed on the edges, and there's a pressure P. Right, so this we start off with our equation, define the biharmonic equation, and then we do integration as we go along. Right, so I wouldn't go through this again here, but at the end now we end up with this expression for the deflection W. Now we have these long terms or these log terms inside here. Now because the plate is a continuous plate, meaning that there will be a point in the center of the plate where r is equal to 0. So when r is equal to 0, and if you type in your calculator log of 0, you will get infinity or some syntax error or something, meaning that the log of 0 is infinite. Obviously we cannot have an infinite displacement, so therefore the constant C0 and C2, because we have another long term here, has to be equal to 0. Right, so that's how we end up with this here. So when C2 and C0 is 0, then the W now equation breaks down to this smaller equation here. So the constants we need to find now is C1 and C3. Right, we did it here by hand. right, where we put where r is equal to a, the deflection is 0. And then we set at the edge now, because it's fixed, the slope is 0. Just like a cantilever or a fixed end beam, the dy dx of the end of the beam where it was fixed was 0. It's the same here. The w dr, which is the slope, is 0. Right? And this allowed us to find C1, and then we could have substituted back into this equation here to find C3. Right? So that's what we did here, and we was able to get C1 and C3. So what we're going to do, we're going to let MATLAB do this for us. Right? So we start off here with our normal entries. Right? So we have our CLC clear all, and then we start off now with sims. Right, so in MATLAB we have symbolic toolbox. We're using the symbolic toolbox. So our symbols, well, everything we have here is symbolic. Right, so we start from the W equation. So our symbols are P for the pressure, D, R, A, mu. Right, mu being, and we will use mu when we come down to find the bending moments. Thickness, C1, C3. Right, you can leave these out for now if you want. And then when that time comes, later on we could just include it. So there's nothing about coming back afterwards and adding symbols here. And next now we're going to enter the W equation. Right, so W is equal to right, so we have entered the equation. Exactly how it is here. Right, so if you click run, you could do this as a check to make sure. So this is the equation here. Right, we did not have the semicolon at the end of the equation, so that it's able to be for us to see it here. And then you could do our command pretty W just to see how it looks and if it matches up. Right, so this is our equation, and you can cross check that now with what we have here. So the next thing we want to do now is differentiate this, because we see here that we needed to find its slope. So for that we use DIFF. We want to differentiate W with respect to R. Right, and we could call this dW dr if you want. Right, now after that now we know that when R is equal to A, the deflection is 0. So we could say, okay, let R equal to A. And then the next command we want to do here now, we want to evaluate this here, this equation, for when R is equal to 8. So we could say W1, for example, or WA, we could put WA. Right, that is just saying that R is equal to A in equation is equal to EVAL, meaning evaluate. So we want to evaluate W. Because we put a value for A here, sorry, a value for R, not a physical value, but we want to change R into A, then we could evaluate back the W where R is equal to A. Right, so if we run this, what we could see here now is WA. You could see where we had the R's before, now we have A's. Right, so that's a easy pretty command again. Right, so where we had before, we have a. So that's what eval does. If it is you put r is equal to 5, well, then instead of a, you would have 5. Right, so you're going to do the same thing for the differentiation. Right, at r is equal to a, the slope is also 0. So we say dw dr, we could put underscore a, is equal to, again, we use the eval. Because we're saying at r is equal to a, the slope is 0. Right, so just like how we substitute that here, we'll do the same here. So again, if we run, we could compare. Right, so we run the pretty command just to have a look at it, how it looks. Right, so we could see here that it matches up to what we have done by hand. So now that we have w, so basically we have this equation and we have this equation. Well, we have this side of the equation at least. Right? So we want to make the two equations equal to 0, like what we did here, and then solve for C1 and C3. Two equations, two unknowns. So for that now we could say, okay, we could say constants is equal now we're going to use something called the solve command, SOLVE. Right, so the solve command works different in the newer versions of MATLAB as compared to the older version, like what it will have in 2010. So I recommend that you use one of the computers that has the latest version of MATLAB, 2020 or 2021. Right, so what we want to do, we want to say solve, and the equations we want to solve is, we want to say w underscore a, right, that's this equation here, is equal to, so we put two equal sign to 0. Same thing for the slope is equal to 0. And so that's the two equations you want to solve. And then next, what we solving for? We're solving for C1 and C3. Right, so this will be our constants here. So we click run. Right, so you can see the constants here in the workspace. So you notice something is a structure, and we talked about structures in a couple of videos ago. Right, so if C1, C3. So you can see this is C1, and this is C3. So it actually solves for the two constants. Right, so we need to pull this out from the structure and be able to use it. Right, so for that, let's recall what it is we did in the previous video. And now let's copy and paste it. Right, so we could recall when we're trying to pull something from a structure, we put the name on the structure, dot, and what it is we want from it. Right, so this is C1, this is C3 here. If we click run, we could have a look at C1 and C3. So C1 is minus PA squared on 8D, and so that's what we have here. Right, again, if you want, we could use the pretty command and call this C1 here. So you can see that's what we have there, minus. Right, you could also press up on the keyboard. When you press up, it will just repeat the last command, and we could change this to C3. So you can see we have C3 here. So there, in a code way, we was able to actually solve for those constants. So in other questions where the constants get really large, it is difficult sometimes, not difficult, but it takes a lot of time, and it's prone to make in human error in trying to make all these substitutions and all that, and trying to solve for the unknowns. So MATLAB takes away that error element from it. Right, so now that we get the constants, right, so we could put a semicolon so we don't need to be seeing that because we know it correct based on what we have here. Right, so the next thing we need to do now is get the W in this form here. Right, so actually substitute the constants and simplify the equation. Right, so over here we had R is equal to A. Remember we had defined that here. So we want it back in terms of R. So what we could do, we could do sims again and R. So what we do, we just kind of rewrite R. So it's no longer R is equal to A. R is equal to this R. Right, and then we could say W is equal to eval now W. Right, so what we did here now, we have C1 and C3 stored in the workspace. So it will actually substitute C1 and C3, what was determined here, into this equation and evaluate W. Right, and we tell in MATLAB also that R is back to R. Right, so if we run this, you could see we have W. So this was the first W with C1 and C3. Now we have W with C1 and C3 values substituted. Right, so if we use PT command here, right, so this is it here. If you want to simplify this further, there's a command called simplify, S-I-M-L-L, simplify. Right, so what that does, it kind of shortens, it does the simplification process somewhat. It doesn't do it perfectly, but it does something. Right, so it kind of cancels out stuff, it pulls factors out, etc. Right, so it pulls it out and it simplifies it to a form that we have here already. So you see it actually gives us the simplified version that we have here. Right, so you can see we got the answer and like similar to what we did in hand. So what we could do here now is that we could actually now type here, we could say W is equal to simplify W. And so that will give us the simplified version. And the next thing we want to do now is differentiate this W now, because now we need to get the moments. In order to get the moment, we need to find d2w dr squared, dw and dr. So we could say dw dr. Right, so we could rewrite these things because we're done with this part already. Well, the code will be finished with it. The code is running step by step. It will find the constants. So we don't need to go back to do this here. Right? So we could actually just copy this here. Right, so it will be differentiation this w with r. Right, and notice we have a d2w dr squared. So we could write a d2w dr squared. Right, and that is where we differentiate dw dr with respect to r. Right, so we have dw dr and then d2w dr squared. And next we could put in our equations for mr and m theta. Right, so mr right, so mu is written as v. Right, so that's why I actually included all these symbolics over here one time. But you could have come afterwards and put it here, it doesn't matter. Right, so that's m theta. Right, so we don't have a theta on the keyboard, I just use small o. So when we run this, Right, so we got our error message here. So we need to sort this out. Actually, the error message is, I think I spent simply fly wrong here. So there's a matter of making that change. Right, so we have MR and we have M theta. Right, so it again is pretty big and cumbersome. We could simplify this further. Let's see if it will make a difference. Okay, so it actually break it down smaller. Right, and then we could just use the pretty command here. And we could compare this now to MR. Right, so P on 16. Right, so it doesn't factor it out like how we did it here. Right, so minus 3r squared minus 3r squared. Mu minus mu r squared minus mu r squared here. A squared mu, a squared mu, right? So it is correct, I just not factor out here. Right, so we need to put in this line simplify just to condense the code a little. Well, to condense the answers a little. Right, so put in simplify and then pretty just to kind of clean it up. Right, so this is MR here, this will be M theta. Right, so minus 3 mu r squared, so we have that here. Right, so we have all the terms. Well, so this is how we got MR and M theta. Right, so the next bit here now is the stress. Right, so the hardest thing is really to get the Bennett moments because the stress equation is pretty much straightforward. So for the stress, it's pretty straightforward. We could just put in the formula as it is over here. Right, so let's copy and paste it from another script. Right, so when you click run, it will just let's say a sigma and a sigma theta. Right, T for theta. Here. Right, we could actually change that further put O, this is for theta. Alright, so that's our stress. Now suppose we want to actually put in values for stress. Then we could say, okay, if we have a problem and the problem is where we have T is equal to 3 millimeters, P is 10,000 pascals, mu is 0.3 and the A is 1. So the radius of the plate is 1. So then we could say now, when we define all these values in the workspace, then we could say sigma R, for example, equation. Right, so before we had everything in terms of A and P and T, etc. Now we're going to actually substitute values. So we could use again the eval function. Right, so let's do for sigma for now. Right, so when we run this, you could see the very long value we get here. Right, so it's one big long value divided by next value. So MATLAB didn't work it out then. MATLAB didn't solve it. They solved the numerator, denominator. They didn't complete the calculation then. Right, so for that now what we could do, we could say okay, sigma R E. So one way to get MATLAB to do it now is actually evaluate that evaluation then. So we could go VPA, which means variable precision arithmetic. So we tell them MATLAB to do some arithmetic first. We could put sig R equation. Right, so we put in this variable. So we wanted to do some arithmetic on that. So if we click OK and we run now, it will look like. So you can see we get some big numbers here, and all in terms of r squared, because remember r is varying from 0 to a. Right, so this still might be good enough because we have 5, 4, 1, etc. 0.666 going. Right, so this might be again might be a bit too cumbersome. 3 significant figures is good enough. So we could specify that. We could put here comma 3. So it will only take the first 3 values of that large number then. Right, we don't really care about, because we're dealing with stress, we don't really care about so much precision in terms of all decimal places and stuff. Right, so by putting 3 now, what we do is break it down to 3 significant figures. Right, so the long values that before now is 5.42 e to the power 8 minus 1.38 by e to the power 9. Right, so we get a nice clean equation for um, sigma r. So that's how we could determine sigma r. We could go further if you want, and we could say, okay, right, so I'll put some semicolons here now because we know what we get in there. Right, we could say let r equal to 0, right, so what we're doing here, we're saying let r take points from 0 all the way to the diameter in increments of 0.01 meters, right, that's every 10 millimeters. And then we could say plot r versus right, so let's see whatever message we got there. Okay, so we need to evaluate. What I didn't do just now was I did not evaluate the equation with the new values of r. So sigma r, we call this values for something, is equal to eval and then our equation. Right? So again, what I would do, I would substitute r values into the equation we just now obtained. Then now we could actually do the plot. You could plot r versus, right, so we could run this. Right, so we could see we have a plot now of the stress now on the y-axis and r on the x-axis. So when at the middle, when r is 0, we have the stress value, and as we move out to the radius, we could see it goes from tension to compression. Right, we could visualize the tension because in the middle of the plate, the bottom is stretching out, which is what we would expect. But as we go to the fixed region now, there will be some compression taking place. Right, so that is really in a nutshell using MATLAB to assist with these type of problems. Right, so you could go on the fix of this plot and put title and put the grid, etc. But again, it shows now that you could use MATLAB to visualize your distribution, your stress distribution within a component.